Hello everyone and welcome back to some more remote learning. In this video, we're going to go more in depth with the derivative function. So how do you calculate the derivative function? Well, we now know how to find, from our previous example worksheet, the derivative using limits at a specific point. But what if we want to know the derivative at multiple different points? It would take us quite a long time to redo that limit for every point we want to know along that same function. So in this worksheet, we're going to go over how to find the derivative function. That way, when we want to know the derivative at a new point along the same exact function, we don't have to redo that limit. So let's use limits now to find the derivative function. And the derivative of a function is f prime of x. Remember in the previous video, we were talking about f prime of a, where a was the point value we wanted to find the derivative at. However, f prime of x is going to be some derivative function, and that's going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. This formula should look very familiar, except as opposed to plugging in a specific a value, we're now plugging in an x variable. That way, when we solve for that limit, it's going to be in terms of x, as opposed to giving us some exact value. Let's go ahead and use this limit definition for example 1. It says for each of the following, find the derivative at the specified points. So in part A, zooming on in, we have f of x, our function, equals x squared minus 3, and I want to find the derivative at -2, 0, and +2. What I'm going to do is to take this derivative function, calculate that, and then plug in my point values. So f prime of x is going to be equal to the limit as h approaches 0 of, I'm going to fill all of this information in. So I want my function of x plus h, meaning wherever there's an x, I'm going to plug in an x plus h instead. So f of x plus h is going to be x plus h squared minus 3. And then from that, I'm subtracting f of x, which we know the function of x, it's given to us. That's x squared minus 3. And parentheses are very important when dealing with this definition because we're subtracting that entire function of x, so it needs to be in parentheses. And that's going to be all over h. Now this is just some polynomial function, so we should be able to cancel out this h in our denominator. So let's go ahead, use some algebraic manipulation to cancel that out so we can plug 0 in for h. Right now we can't because if we plugged in 0, our denominator would be 0. So let's do some simplification. So this is going to be equal to the limit as h approaches 0 of, lots of times in order to simplify, we have to expand. But right off the bat, this -3, when I subtract a -3, that's -3 plus 3, so these 3's will cancel out. So right away, I already have something that's canceling out. Now I'm going to expand out this binomial, x plus h squared. That's going to be x squared plus 2xh plus h squared, and I'm still subtracting this x squared. And that's going to be all over h. Now you can see that x squared cancels out with x squared, and in my numerator I have an h that's multiplied to all of my terms. So I'm going to rewrite this so you can see how the h will get canceled out. So we're going to have the limit as h approaches 0 of h times 2x plus h, and that's all over h. Now look, h cancels out, I can plug 0 now right on into my limit. So the limit of 2x plus h as h approaches 0 is going to be 2x plus 0, which equals 2x. So this right here is the derivative of my function, 2x. So if I were to graph this x squared minus 3, the slope of my tangent line, anywhere along that function, I can find by plugging in my point value for x, and the derivative is going to be 2x. that slope of the tangent line is 2x. So if I want to know the slope at -2, well, I'm going to plug -2 right on in. So we'll have 2 times -2, that's going to be f prime of -2. 2 times -2 gives me a -4. So we get -4 when x is equal to -2. What about 0? F prime of 0, plugging 0 right on in for x, we're going to get 2 times 0, which gives us 0. Ah, slope of 0, what technically is that? That's going to be a horizontal tangent line if we were to create that equation of the tangent line. And then lastly, plugging in 2 for x, f prime of 2, that's going to be equal to 2 times 2, which gives us 4. And that's the derivative at each of those given x values. And again, remember that previous worksheet, we did f of a plus h minus f of a all over h, the limit of that as h approached 0. Same concept here, except we're leaving x as a variable so we can plug in our a values later as opposed to plugging them into the limit itself. Let's continue on to part B. In part B, our function is 6 square root of x. So when calculating that derivative, we're going to have f prime of x equal to the limit as h approaches 0 of, well, f of x plus h minus f of x all over h. So we're plugging in x plus h into our function. So we're going to have 6 square root of x plus h, and then we're going to subtract f of x, which is 6 square root of x, and that's all over h. Now we have a square root in our numerator, and we're trying to cancel out this h in our denominator. We're going to be multiplying by the conjugate. But before I multiply by the conjugate, I'm going to make this easier and pull out my greatest common factor in my numerator, because each term has a 6. So I'm going to rewrite this as the limit as h approaches 0 of 6 times the square root of x plus h minus the square root of x all over h. So when I multiply by the conjugate, I'm going to be multiplying by 1, the conjugate over itself. So that's going to be the square root of x plus h plus the square root of x all over the square root of x plus h plus the square root of x. Now we'll have the limit as h approaches 0 of, our numerator is 6, times, when I distribute that out, that middle term gets canceled out because I have a plus, and then I'm subtracting that same exact term. So I'm just going to have a squared minus b squared. So my a squared is going to be square root of x plus h times square root of x plus h, which is x plus h. And then I'll have negative square root of x times a positive square root of x. That's going to give me minus x. And that's all over h times that conjugate, square root of x plus h plus square root of x. No need to distribute that h through, because remember, that's what we want to get canceled out, because plugging in 0 for that is giving us issues. It makes the function undefined, which we don't want. But now you can see that when I cancel out my x's, all I have in my numerator is 6 times h. So because I have h multiplied by everything in my numerator, and I have h multiplied by everything in my denominator, my h will also cancel out. So my limit is going to be the limit of 6 over square root of x plus h plus square root of x as h approaches 0. Now I can plug h right on in, because if I plug 0 in for h now, my denominator is not going to be undefined. So plugging 0 on in, I'll get 6 over the square root of x plus 0 plus the square root of x, which is going to be 6 over square root of x plus square root of x is going to be 2 square roots of x. 6 over 2 gives me 3. So I'm going to have 3 over the square root of x. So that is my derivative function. The derivative at any point along my original function, I just plug my x value in to get the derivative. So the first derivative we're going to find is f prime of 0. If I take 0 and try to plug it in, I'll get 3 over the square root of 0. Can't do that. So actually my derivative at 0 is undefined. So my derivative at 0 is undefined. I cannot plug 0 in for this function, so the derivative simply doesn't exist. It's undefined. But I can plug in 1. If I have f prime of 1, that's going to be 3 over the square root of 1, which gives me 3 over 1, which is 3. So I get undefined for my derivative when x equals 0, and I get 3 for my derivative when x equals 1. And think about it. Plugging in 0, our function is defined, but our derivative is undefined. But logically that makes sense, because think about the values we cannot plug in for x. The square root of x, the domain is from 0 to infinity. That's the interval of continuity. It does not exist for values less than 0. So when we're at the point 0, we can't figure out that derivative because there's nothing before it. There's no values to the left of 0 that help us find that derivative. So because there's no values to the left, when we're at 0, we can't definitely say what that slope is. Therefore, it's undefined. Now, later in this example video, we're going to go over differentiation and how that relates to continuity. So we'll go over this type of example more in depth and why the derivative is undefined. But for now, let's continue on. So let's go ahead and actually talk about that now. So differentiation and continuity, how do they relate? Well, if a function is differentiable, meaning that we can take the derivative of it at a given point, then the function is continuous at that point. But let's talk about exactly what that statement means and apply it in the following example. So if a function is differentiable, then the function is continuous. This does not go the reverse. If a function is continuous, that does not mean necessarily that it's differentiable. Actually, if a function is not continuous, so if it's not continuous at a given point, then that function is not differentiable. So essentially, just because a function is continuous does not necessarily mean it's differentiable. However, if a function is not continuous, then we know for a fact it's not differentiable. But let's look at example 2 and go over a couple different cases of what makes a function differentiable or not, and what makes the function continuous or not. So we know that if it is differentiable, then it is continuous. And if it's not continuous, we know that it's not differentiable. So let's look at the given points below and state whether the function is differentiable and or continuous. So looking at A, we have some function f of r, where our function is r squared minus 1 over r plus 3. And we're trying to figure out if it's differentiable and or continuous at r equals -3. Well, plugging in -3 for r, what happens to our function? Are we continuous at that point r equals -3? No, we're not, because when we plug in -3, our function is undefined and not continuous. So in example 2, part A, this is a case where the function is undefined. And because the function is undefined, we are not continuous. And because we're not continuous, we're not differentiable. We are unable to take the derivative at that point. That's not saying that we can't take the derivative at other points along the function, it's just we cannot take the derivative at that specific point. Let's continue on to B. In part B, we have the cube root of x, and we're trying to figure out if it's differentiable at x equals 0. Well, let's look. If we plug 0 in, can we take the cube root of 0? Yeah, we totally can. So we are indeed continuous, but are we differentiable? So just to save time on this worksheet, as opposed to trying to calculate the derivative using the limit, I'm going to tell you what this derivative is. The derivative of h of x, the cube root of x, is going to be 1/3 times x to the negative 2/3. 1/3 x to the negative 2/3 is 1/3 x to the positive 2/3, putting that in the denominator. So if this is the derivative, this is h prime of x, well, if we plugged 0 in for x, what would happen? Our derivative would be undefined. So we're continuous and we're not differentiable, because at that point x equals 0, our derivative is not defined. So we're continuous and we're not differentiable. So again, that's showing that continuity does not imply differentiability. However, differentiability does imply continuity. If we were differentiable, then right away we can say we are continuous, or negate that reverse. If we're not continuous, then we're not differentiable. But if we are continuous, we can't say that we're definitely differentiable. We got to do some work to figure it out. So far, the two different cases we've covered is we're not differentiable if we're not continuous, and we're not differentiable if we have a vertical tangent line. And we're going to go over one more case. Let's look at g of x. G of x is equal to the absolute value of 2x. And we're trying to see if it's differentiable at x equals 0. Well, we can plug 0 right on in, so we know it is indeed continuous. However, let's think about the graph of the absolute value of 2x. If we're looking at the graph, we have a negative slope to the left of 0, and then at 0 our slope immediately changes to a positive slope. So right here we have a corner. The slope, or the derivative, is constant before that, and then all of a sudden it immediately switches. But what is the derivative at that point? Does it take on that negative slope? Does it take on that positive slope? Well, it's neither. When we have a corner, or if we have something that looks like a cusp at a sharp point, or a corner, a cusp or a corner, we are not differentiable. So we're continuous for C, but we're not differentiable. And there we have it. Those are the three main cases where we're not differentiable. One, we're not continuous. Another one being that we have a vertical tangent line. And then next, when we're at a corner or a cusp, we are unable to take the derivative. In the next part of this worksheet, we're going to jump into an introduction on graphing the derivative now that we understand when a function is differentiable and not. Now that we understand how to find the derivative and when we can find the derivative, we're going to start graphing. This will help us make connections and relationships between functions, those original functions, and their derivatives. So for each of the three following pictures, we're going to graph the derivative on the same exact graph. Now, for this first graph, I actually used my same function from up above, and that was that f of x was equal to x squared minus 3. And if you remember, we found the derivative function was f prime of x, that was 2x. And we found the derivative at a couple different points. We found the derivative at -2 and got that it was -4. We found the derivative at 0 and got that it was 0. And we had also found that the derivative at 2 was equal to 4. And again, this is all from the example up above, example 1, where we calculated the derivative of x squared minus 3 and found the derivative at a couple different points. So let's just go ahead and think about how that derivative relates to the function. Well, if our function is decreasing, what kind of slopes are my tangent lines going to have? My tangent lines are all going to be negative. If my function is increasing, my tangent lines are all going to have what kind of slope? A positive slope. So while our function is decreasing, we have a negative slope. While our function is increasing, we have a positive slope. And at that point where we switch over from a negative slope to a positive slope, as long as it's a smooth transition and not a corner of a cusp, our derivative at that point is going to be 0. And we confirm that. F prime of 0, when x is 0, we're at -3 for our function, but our derivative is 0. So if I'm trying to fill out this derivative graph, I'm going to go ahead and plot 0, 0. I'm also going to plot my point -2, -4, because when I was at -2 in the x, wherever my function was, that tangent line had a slope of -4. So I'm going to graph that on here. -2, and then -4 would fall at about right here. And then at 2, we're at about 4. So probably up here. I know this goes off the graph a little bit, but that's okay. And maybe since we have the function, let's do another point or two. When we're at -1 in the x, f prime of -1, the slope of the derivative is 2 times -1, which gives us a -2. So our derivative has a point -1, comma -2. So when I'm at -1 in the x, I'm at -2 in the y. And if I find f prime of 1, when I'm at 1 in the x, I'll be at a +2 in the y. So you can kind of see if we were to attempt to connect these points, we're going to get a straight line. And that's because our derivative function is a linear equation. 2x plus 0. Essentially, if you think about it as y equals mx plus b, we have a slope of 2 and that y-intercept of 0. So it makes sense that we get a linear equation. However, for the next couple of examples, we're not necessarily going to have the function. We're just going to be looking at the graph. But again, all we need to do is think about what the slope of our function is at that point and attempt to graph that. So let's move on to our next graph. So here, we're looking at some piecewise function. And remember, what did we say? At a corner or a cusp, our derivative is undefined. So I have two separate corners at -1 and at a +2 in the x. So I know I'm going to have an undefined derivative at those 2 points. But let's think about what that means. Let's look at our function to the left of that x value of -1. To the left of the x value of -1, our function is what? Increasing or decreasing? It's increasing. So that slope is positive or negative? It's positive. So we have a positive slope, so we would expect our derivative to be above the x-axis when that original function is increasing. And because it's linear, the slope along that piece up until -1 is always the same. So when we graph the derivative, it's going to be constant. So let's take a look. For every 1 in the run, it looks like we go 1 in the rise. So if we have rise over run, 1 over 1, that's a slope of a +1. So from -infinity, I'm assuming that this graph continues on in both directions, from -infinity up to -1, we have that same slope of +1. So in order to graph that, I'll do my derivative in blue. I'm going to find 1 and draw a horizontal line up until my point -1. Now at -1, that derivative we said was what? It was undefined. So I'm going to put an open circle around that -1. Because I have that corner there, my derivative is undefined at -1. Now, let's move on to our next segment of this piecewise function. The next segment goes from -1 to +2 in the x. So from -1 to +2, what does our slope look like? Well, our function is horizontal, and if our function is horizontal, that means that the slope is equal to 0. And it's equal to 0 from -1 to -2. So when we graph this from -1 to 2, we're going to draw our line on our axis. From -1 to 2, we have a 0 slope. So the derivative needs to reflect that and needs to also be 0. And again, we're undefined at -1 and 2, so open circles around those. And then lastly, after that, at x equals 2, our function changes, and now our function is decreasing. So what kind of slopes do we have if our function is decreasing? That's negative slopes. And because it's linear, our slope is going to always be the same. So we just have to figure out the slope of this line and then graph that constant derivative. So for every, let's take a look at this. I'll try to find my next point where it intersects grid lines, and that looks to be at approximately 3, -1. So you can see that if I go down 1, 2, 3 in the rise, I go over 1 in the run. Change in y over change in x, going down 3 over a +1, -3 over 1, that's going to give me a slope of -3. So remember, I have an open circle when x is equal to 2, because my derivative is undefined at 2, but then I continue on making sure my derivative is constant at -3. So that's how you would graph the derivative, especially when dealing with linear equations. The derivative is always going to be constant because the slope of a linear equation isn't changing. Let's move on to our last example. Now this one's going to be a bit trickier because we don't have some function to be able to say exactly what the derivative is at any given point. However, we have some different things we can label to help us think about the derivative. So from -infinity up to 0, what is my function doing? My function is decreasing, so I would expect the derivative to be negative. And then from 0 to, it looks like about 3.5-ish to this point here, my function is now increasing. So my derivative is positive. And then again, from that 3.5 on, my function is then decreasing. So I know that derivative is again negative. So if my derivative goes from being negative below the x-axis and then positive above the x-axis back to negative below the x-axis, I'm going to cross over the x-axis twice, which means at 2 different points of time, my derivative is equal to 0. And when my derivative is 0, essentially that means I have a horizontal tangent line, which we can kind of envision on this graph. When our derivative changes from negative to positive, that's when we have a horizontal tangent line, which it looks like it occurs at 0 and at this, let's call this 3.5. So right away, I'm going to make a mark at both 0 and 3.5 for my derivative, because I know at each of those values, my derivative is negative. Now between those two, I said that my derivative was positive. And if we think about the slope starts out and then it gets steeper, so the slope is greater, and then it all of a sudden gets less steep again. So our derivative is going to be positive, it's going to be larger positive values, and then it's going to go back to smaller positive values, which makes sense. So near 0, we're going to have where that derivative was those smaller positive values, and then we're going to hit our peak, and then we're going to go back towards 0 again. So touching that picture up a bit, we know between 0 and 3.5 our derivative is positive, and there's no jumps, there's nowhere that our derivative is undefined. So our derivative is going to be nice and continuous because it's defined everywhere. So we have smaller positive derivative values, and then when we get to that peak, and then if we kind of think about continuing this along, again, our derivative has a smaller slope closer to 0, and then it has a steeper negative slope from there. So I'm going to continue this like so. So my steeper slope values are further away from when my derivative equals 0, and same on this side as well. You can see that my slope has smaller negative values and then gets steeper and steeper. So greater and greater negative values for my derivative. So I'll continue this like so. And that's roughly how we would draw the derivative for this function. In a later example video, we're going to go over graphing the derivative and graphing higher order derivatives as well, and relating all those parts together to get a more accurate picture or diagram of the function and how it relates to its derivatives. And I know that we were just estimating for these graphs, but you should be fairly comfortable with graphing the derivative of linear functions, because remember, that's going to give you constant derivatives, so you should be able to find the slope and graph that. And then for other polynomial functions, you should be able to get at least the rough picture, knowing when the derivative is negative, when it's positive. So figuring out when we have those horizontal tangent lines, when the derivative is 0, is going to be very helpful for graphing. So the big takeaway from this worksheet now is that we can finally calculate the derivative function and find the derivative at any given point along a function. And we also know that differentiability implies continuity, but just because a function is continuous does not mean that it's differentiable. Now, speaking of the derivatives of a function, as of now we've only learned how to calculate that by taking the limit. However, in the next video, we're going to get into some rules for differentiation. And those rules will allow us to find the derivative without applying the limit. But it's still important to remember that limit definition for that derivative to give you an appreciation and an understanding of what the derivative is. But now we're going to jump in some rules of differentiation to make calculating the derivative a lot easier. So continue on to the next video to get started with those rules. But before you do that, keep on practicing. And until the next video, good luck with your online learning.